Modern data science is largely built on a single, dominant assumption. More data requires deeper, increasingly complex neural networks to process it. That principle holds up when training an algorithm to generate natural language or recognize objects in a photograph. But when applied to highly structured operational fields like renewable energy management, this default reliance on deep learning creates massive computational inefficiencies. Take the domain of solar power forecasting. To balance day-ahead electricity markets, modern smart grids rely on predicting photovoltaic output down to the minute. Researchers analyzing these grids have found that forcing deep learning architectures onto this specific forecasting problem requires expensive server time and steep memory costs that may be mathematically unnecessary. This raises a specific question for energy engineers. Can a basic, highly tuned linear model actually match or even outpace the most complex deep learning architectures currently available? In the rush to adopt the most advanced AI architectures, engineers often ignore the heavy cost of computational complexity, choosing brute force over mathematical elegance. To test this, researchers established a baseline using a continuous 20-year hourly dataset sourced from NASA and SES Design, tracking weather and solar conditions in Antalya, Turkey. The dataset is built of highly structured tabular variables: solar irradiance, ambient temperature, wind speed, and historical power output. As this permutation chart shows, a few distinct measurements dictate the final output. The dominant blue bar on the left reveals that incident solar radiation carries the overwhelming weight of the predictive importance, followed by solar altitude. With the data set locked, researchers established the parameters for direct comparison. 12 distinct machine learning and deep learning models were pitted against the exact same 2 decades of data. The competitors ranged from simple k-nearest neighbors and random forests all the way up to multi-layered deep neural networks. The model that achieved the highest predictive accuracy was Ridge Regression, a computationally lightweight, linear approach. Achieving the highest accuracy on a tabular dataset relies on finding the perfect mathematical fit for the data's inherent shape, rather than simply deploying raw processing power. Predictive accuracy is only one half of the equation. Day-ahead energy markets require real-time, instantaneous load balancing calculations to function. This introduces 2 metrics of computational cost that dictate whether a model is viable in the real world: memory usage and training time. If we knot the heavier ensemble competitors, the resource drain is clear. Random forest demands a 63.4 megabyte footprint. Deep learning architectures set even higher, requiring multi-hour tuning and intensive memory. Then we plot Ridge Regression. It pins perfectly to the origin point. It operates with near-zero memory usage and requires 0 minutes of baseline training time. Deploying a 0 megabyte model means it can be embedded directly into local microgrids, making it vastly more scalable than centralized deep learning server farms. One might assume that such a low computational footprint would lead to higher error rates or failures on complex edge cases. The Ridge Regression results prove that heavy computational cost does not lead to higher intelligence.
But getting a lightweight model to outsmart a deep neural network depends on a secondary phase of development. That phase is hyperparameter optimization, the process of tuning the external settings that dictate how an algorithm actually processes and learns from the training data. The benchmark study exposes a frequent engineering error, treating this optimization step like a one-size-fits-all process. The first tuning method tested is the genetic algorithm, deployed via a tool called teapot regressor. This algorithm excels at exploring massive, unpredictable search spaces. It is the superior choice for optimizing certain models, specifically k-nearest neighbors and support vector regressors. Then there is the second tuning method, the grid search algorithm. Grid search takes a systematic approach, testing every single parameter combination on a predefined matrix to remove all randomness from the search. Applying the exploratory genetic algorithm to a Ridge regression model yields subpar results. But a systematic grid search forces the model to test every parameter combination, eventually finding the exact configuration that maximizes its predictive accuracy. Because Ridge regression is inherently linear, the grid search forces it into perfect alignment. This specific tuning pairing is what pushes the model's accuracy past the multi-layered deep learning architectures. Matching a model to its specific mathematical strengths
yields higher accuracy than simply choosing the most complex algorithm available. To verify the Ridge model is truly superior to its deep learning competitors, we have to look past the aggregate scores and analyze its exact margin of error. The tuned Ridge regression achieves an R-squared score of 0.9998. This indicates an almost flawless capture of the variance within 20 years of solar data. The dense concentration sits directly in the mid-range power output area, proving the model handles high-stakes daytime operating conditions accurately. This reliability is confirmed by the residual diagnostics. In the bottom left QQ plot, data perfectly aligns with the red line, proving a strict normal distribution. On the bottom right timeline chart, the maximum spread of those errors is a minuscule plus or minus 44 watts per square meter. The model rarely misses, and when it does, it misses cleanly and predictably. This data firmly closes the case against the necessity of deep learning for this application. When analyzing highly structured, continuous tabular data like weather patterns and solar irradiance, deep learning is frequently overkill. Deploying a massive neural network on tabular data often wastes computational power hunting for complex relationships that do not exist, leading to potential overfitting. Matching the correct optimization algorithm to a model's specific mathematical architecture is the hallmark of an expert data scientist. This efficiency scales directly into our physical infrastructure. The smart grids managing the energy transition must make load-balancing routing decisions in milliseconds. They cannot wait for bloated, computationally heavy models to finish their logic. Highly optimized linear models like Ridge Regression are the unseen, lightning-fast workhorses of grid management. As these forecasting systems move from the lab to the grid, efficiency becomes the primary metric of success. The most effective solutions aren't defined by their complexity, but by their ability to solve the problem with the least amount of friction.